Welcome to our course. In this video, we'll explore the fundamental differences between machine learning used in academic research and machine learning deployed in industry production systems. Understanding this distinction is crucial for anyone transitioning into a professional ML role. Let's get started. Welcome to our training video. Today, we are exploring the critical differences between machine learning in research and ML used in industry production. When you hear about ML, you often think of complex math or coding the algorithms, such as deciding whether to use a decision tree or a neural network. This part is certainly the most fun step for many practitioners. However, in a real company or application, the algorithm is actually only a small part of the whole system. For absolute beginners, think of an ML system in production as a full machine, not just one small part of the engine. This full machine includes everything from the data input to the final user output. These systems rely on business objectives and must be highly reliable. They need extensive support, including the infrastructure and data management logic, often called the data stack. We need to understand this whole picture to succeed in implementing ML solutions. This diagram shows how the initial algorithm is just one piece of a much larger machine learning system. In a research or academic setting, we often focus mainly on the algorithm or model component. But in production, the overall ML system is much more extensive. It must integrate with the business logic, which determines why the system exists in the first place, based on real-world objectives. It needs the data stack and features components, which handle acquiring, cleaning, and transforming the messy real-world data. Finally, the infrastructure and monitoring block ensures the system runs smoothly, reliably, and consistently for actual users. Remember, the algorithm is inside the red box, but the blue boxes show everything else that is necessary for deployment. This holistic view is the first step in understanding production ML. In the research environment, the main goal is often to prove that a new model or technique works very well, usually aiming for the best possible score on a known, standardized test dataset. This is called achieving the state of the art, or SOTA. However, when you move to industry, the goals shift dramatically. The primary focus is always on business objectives. For example, a data scientist might increase model accuracy by a tiny fraction. But if that change does not move key business metrics, like increasing sales or improving customer satisfaction, the effort might be wasted. When designing production systems, we must ensure they meet certain enterprise requirements. These include reliability, meaning the system always works correctly, even if hardware fails. Scalability ensures the system can handle growth, such as millions of requests per hour. Maintainability means different teams, like engineers and subject matter experts, can easily work on and update the system. Finally, adaptability means it can adjust to changing environments and user needs. This class diagram highlights the difference in priorities between research ML and production ML. Research ML mainly focuses on achieving the best possible score, known as SOTA performance, typically using static, known benchmark datasets. The algorithm itself is the main point of study. Conversely, production ML's main goal is driven by improving core business metrics in a real, ongoing environment. It must handle dynamic, constantly changing data. The key focus here is ensuring the system's reliability and ability to scale up efficiently. While both activities use machine learning models, their requirements, and therefore their engineering priorities, are fundamentally different. Reliability in production is often more valued than squeezing out the last fraction of accuracy in a research setting. Production systems must support the company's continuous operations. The type of data used is one of the biggest distinctions. In an academic or research setting, the datasets are typically very clean. They are often static, meaning they never change, and everyone knows the expected quirks. This setup allows researchers to focus purely on algorithm development. However, production data is almost the opposite. It is messy, noisy, and complex. It's often unstructured, meaning it doesn't fit neatly into tables. Crucially, real-world data is constantly shifting. This shifting means the core assumption learned in school, that the new data the model sees will look exactly like the training data, is often incorrect in the real world. This divergence or difference between training data and live data is called a data distribution shift. If this shift occurs, the model might not generalize well, leading to poor predictions. A specific failure related to this is called train-serving skew, where a model trained on clean data performs poorly when deployed on real messy data. The goals for computational power also diverge. In a research setting, practitioners are focused on fast training. They often run dozens or even hundreds of experiments, so they need their training process to be quick, so they can iterate rapidly on new ideas and architectures. They aim for high throughput in training. However, when a model is deployed to users in production, the priority shifts entirely to fast inference and low latency. Inference means the process of generating a prediction for a user. Low latency means getting that prediction quickly. If a large language model, which can have billions of parameters, takes too long to respond, the application becomes useless. Imagine an auto-completion feature on your phone. If it takes even 1 second to suggest the next word, you would already have typed it yourself. This long delay, or high latency, kills the user experience and makes the product unusable. Therefore, speed and memory efficiency during prediction are far more critical than training speed in a production environment. This requirements diagram clearly maps the primary computational requirements. In research environments, the primary need is to prioritize training speed. This allows researchers to rapidly iterate and test new algorithms, optimizing for efficiency during the learning phase. Conversely, in production, the critical requirement is prioritizing inference speed. Inference is when the model generates a prediction for a live user. If this process is slow, it directly harms the user experience. The speed of prediction, known as latency, must be very low for applications like language translation or recommendation engines to be useful. If the model is slow to predict, it doesn't matter how accurate it is, as the user will simply not wait for the response. Thus, production engineers focus on optimizing the deployed model for quick computation. In traditional software engineering, if you write a program, you primarily focus on testing and versioning the code itself. If the code works today, it should work tomorrow. Machine learning systems introduce massive complexity because they rely on data, which changes constantly. Therefore, an ML system must test and version not just the code, but also the raw data, the processed features, and the trained model parameters. It is much harder to version massive datasets than it is to version a piece of code. Unlike a traditional project that follows a straight line from coding to deployment, ML in production follows an iterative process or a cycle. This cycle involves defining the project, engineering the data, developing the model, deploying it, monitoring its performance, and then reanalyzing the business impact before starting the cycle over again. Production ML requires managing all these steps in a cohesive, complex pipeline. This flow illustrates the iterative process for developing an ML system in production. This is a continuous cycle, unlike a one-time script. It starts with raw data, which is then processed through data engineering and feature engineering. Next is the core ML model development stage. Once the model is ready, it enters the deployment stage to serve live predictions. The cycle continues into monitoring and continual learning, which tracks performance and detects failures, like data shifts. Finally, business analysis determines the system's impact on business objectives, feeding back insights to improve the data engineering process. This constant loop highlights that deployment is not the end, but the start of continuous maintenance and improvement necessary in production environments. Interpretability means understanding exactly why a machine learning model provided a specific output. In research, if a complex model, such as a large neural network, achieves the highest accuracy, researchers might often overlook interpretability, especially if forcing the model to explain itself reduces performance. However, in industry, interpretability must be considered. First, it is essential for responsible AI. If a model is used for high-stakes decisions, like loan applications or medical diagnosis, you must ensure it is fair and unbiased. Without transparency, it's a black box dilemma, making it difficult to debug where biases originate. Second, interpretability is vital for maintenance and trust. Developers need to be able to debug failures by tracing the decision path, and users or regulators may demand a right to explanation for algorithmic decisions, especially in critical applications. For example, if an automated grading system perpetuates bias, the system developers must be able to explain the source of that unfairness, which is nearly impossible with a complex, uninterpretable model. This class diagram highlights the conflict regarding interpretability. Research focus generally prioritizes high accuracy, often tolerating low interpretability in complex models. However, in production focus, we strive for both high accuracy and high interpretability to ensure responsible AI. High interpretability supports critical requirements like debugging, ensuring the model's inner workings are clear for maintenance. It also addresses regulatory compliance and builds user trust. Algorithms like decision trees are transparent because they show the variables' relationships to a given output, but neural networks are often opaque and suffer from the black box dilemma. Because production systems make real-world decisions affecting users' lives, being able to explain the reason behind the decision is non-negotiable. The required skills differ significantly. In academia, success usually requires deep knowledge of ML algorithms, probability theory, and complex statistics. Data scientists and researchers focus intensely on modeling and mathematical proofs. However, MLOps, or ML in production, needs operational expertise, often shortened to ops. This includes essential engineering tasks like using containers to package models, managing distributed computing resources, and orchestrating complex job workflows. Because one person rarely has all these skills, production environments rely on cross-functional teams. This means groups must collaborate, including data scientists, software engineers, DevOps specialists, and subject matter experts, like doctors or lawyers, who provide essential domain knowledge. Since infrastructure work requires a very different set of skills than data science, successful companies invest in robust tools to automate these operational tasks. This abstraction allows data scientists to become end-to-end owners of the ML workflow, without needing to become experts in complex infrastructure like Kubernetes. This mind map shows the 3 key types of expertise required for ML in production. ML expertise, usually held by data scientists, focuses on modeling, algorithms, and metrics. Domain knowledge is provided by subject matter experts, which is critical for tasks like labeling and ensuring data quality. Crucially, the ops expertise, held by ML or DevOps engineers, handles the infrastructure, including scaling and using containers like Docker. In production, these areas must connect through MLOps, as ML engineers need to coordinate with platform teams to acquire the data and computing resources needed for model training and serving. Relying solely on ML expertise is insufficient. The biggest challenges often lie in engineering and operationalizing the continuous workflow. We have covered the main differences between ML in research and ML in industry production. Research typically focuses intensely on the algorithm's performance using fixed data, treating the process as a singular, successful experiment. Production, however, is a continuous engineering effort. It requires a holistic system view, addressing complexity across data, infrastructure, and business logic. The challenges shift from finding the best algorithm to building a reliable, cost-effective system that can handle constantly changing, messy data. We saw that production requires fast prediction speeds, strong interpretability, and continuous updates. Remember that if an algorithm is deployed into a larger system, simplicity is key, as software engineering aspects like reliability, predictability, runtime, and memory requirements gain high relevance. The future of ML success in the industry lies in mastering MLOps and the infrastructure needed to support this constant, iterative cycle of development, deployment, and monitoring. This final diagram summarizes the core difference. The research focus is characterized by achieving SOTA accuracy using static benchmarks. This is often viewed as a closed loop, focused on algorithmic improvement. In contrast, the production focus revolves around achieving real business impact using dynamic and shifting data. This leads directly into a process of continual iteration, which must prioritize high reliability and adaptability for the end user. Industry ML is not merely about achieving a great score once. It is about maintaining performance and reliability indefinitely, while continuously managing the risks introduced by real-world data and complexity. Understanding that ML production is fundamentally an infrastructure challenge is the most important lesson when moving from the lab to the real world.